In this video on probability, we'll be talking about theoretical probability, experimental probability, expected frequency, and fairness. Let's start by talking about theoretical probability. This is the classic probability that we've been calculating so far in our probability questions. And it follows the formula that the probability of an event, which we can write as PE, equals to the number of favourable outcomes over the total number of possible outcomes. This type of probability calculation is fine if we have what we can call a God's eye view of what's happening in a question. And what I mean by this is that it requires us to know how many favourable outcomes there are and how many possible outcomes there are. If we don't know these, then it's not possible to calculate the theoretical probability. And so it can be difficult or impossible even to calculate this in complex real-world situations. And so this is where experimental probability can come in. Experimental probability is when observation is used to estimate probability. Under this model, trials are conducted and the number of favourable outcomes are recorded. From these observations, relative frequency is calculated. And relative frequency is calculated as the number of favourable outcomes observed over the number of trials conducted. The number of trials conducted can be called our sample size. And the larger the sample size, the more accurate the experimental probability. And this makes sense because the results of 100 experiments are going to be more reliable than the results of one. The phrases relative frequency and experimental probability are fairly interchangeable. In line with the idea that an increased sample size gives us a more accurate experimental probability, if we were able to conduct an infinite number of trials, then experimental probability should match theoretical probability. So here's an example. Sally and Emma play several tennis matches and record the results. Sally wins 7 of the first 10 matches and Emma wins the next 6. We want to estimate the probability that Emma wins the next match. It's clear in this question that we want to use experimental probability, and we'll do that by finding the relative frequency with which Emma wins the tennis matches. Relative frequency is found by finding the number of favourable outcomes observed over the number of trials conducted. In this case, a win for Emma is considered a favourable outcome. Emma won 3 of the first 10 matches and then the next 6 matches, so in total she's won 9. And the number of trials conducted in this case is just the number of matches that were played in total, which is 16. Notice that in this question, we were asked to estimate the probability. That's because this experimental probability isn't set in stone and might change if we were to conduct further trials or if the girls were to play further matches. Don't forget that a larger sample size gives a more accurate estimate of probability. So here's your question. A student records the colours of cars that pass the school over the course of an hour. 28 of these are red, 32 are silver, 15 are blue, and 50 cars are other colours. So there's 2 things that I want you to find. First of all, the relative frequency of blue cars during this time. And then secondly, estimate the probability that the next car to pass is neither red nor black. So pause the video here, try this question yourself, and then play to see if you're correct. So first of all, we want to find the relative frequency of blue cars during this time. And this will be the number of favourable outcomes observed, in this case blue cars, which is 15, over the total number of trials conducted. And in this case, that's just the total number of cars observed, which is 115. You can cancel this if you like to 3 over 23. Don't forget that this relative frequency doubles as our experimental probability, or an estimate of the probability that a blue car will pass. Secondly, we want to estimate the probability that the next car to pass is neither red nor black. Oh, I need to make a change to that. I never wrote black down as an option. That was very clever of me. Right, I'm making an executive decision there and I'm changing silver to black in the question. Pause again for a second, give that a bash and see what you get. Okay, so this time my favourable outcomes are the outcomes where I don't get red or black. So that means blue and other will do me. In that case, the number of favourable outcomes observed is 55 and the number of total outcomes observed is 115. In this case, we can cancel our answer to 11 over 23 if we like. Our next heading is expected frequency. This is how often we expect a particular outcome to occur out of a number of trials. And expected frequency has a formula, which is probability times the number of trials. And the probability in this formula can be theoretical probability or experimental probability, depending on the question and what happens to be appropriate. So here's a very simple example. This spinner is spun 600 times. How many times would we expect it to land on yellow? So we know that our formula for expected frequency is the probability times the number of trials. So we have to establish probability and number of trials before we begin. The probability of yellow here can be calculated as a theoretical probability because I can see the number of outcomes that are possible, and I can see that each of those colours takes up 1/3 of the spinner. So the probability of yellow in this case is 1/3. The number of trials in this case just means the number of times the spinner is spun. And of course that's 600. So in this question, the expected frequency of yellow is 1/3 times 600, giving us 200. This expected frequency is a prediction of what might happen in the future. But it's just important to note that it's not set in stone. If I did spin the spinner 600 times, it might not give me exactly 200 yellows. However, 200 is the best estimate I can make in advance of what might happen in that situation. So here's a question for you. For this, we're going back to Sally and Emma and their tennis matches. So we have the same information as before about their wins, and this time we want to know if they play 50 more matches, how many of these would we expect Emma to win? Pause the video here while you calculate that, and then play to see if you're correct. So again, we'll note that expected frequency equals probability times number of trials. And of course, this time our probability is going to be an experimental probability. And as we've previously calculated, the probability that Emma wins is 9/16. I want the girls to play 50 more matches. So in this case, the number of trials is 50. And then I'll use these values to calculate expected frequency. So in this case, the calculation is 9/16 times 50. That results in 28.125. But of course, you can't win a bit of a match. So we'll round our answer to 28 wins. The last section of this video relates to fairness. This is particularly important in games of chance. For example, games that depend on the roll of dice. An unfair game is biased. For example, regular dice may be weighted in order to give back a particular result more frequently. We can assess fairness in a couple of ways. First of all, we could do that by comparing theoretical probability and relative frequency, or by comparing actual frequency and expected frequency. So here's an example. This spinner is spun 600 times with the following results. Pink has got 280 times, yellow 140 and orange 180. Is the spinner fair? And explain our answer. To answer this question, I'm going to extend my table in order to compare the theoretical probability of the results of a fair spinner and the observed outcomes that we've seen in this question. We've observed a result of pink 280 times, yellow 140 times and orange 180 times. From these we can calculate the relative frequencies of the outcomes, and because we're going to want to compare them with other values, it's best to write them as decimals. The relative frequency for pink is 0.467, for yellow it's 0.233, and for orange it's 0.300. Next I'm going to record the theoretical probabilities. These are the probabilities that would arise if the spinner was fair. And again, in each case, because I'm going to want to do comparison, I'm going to write these as decimals. The most striking deviation from the theoretical probability occurs with pink. So I'll focus on this for my answer and explanation. I can see the relative frequency is much bigger than the theoretical probability here. But what I'd like to do is I'd like to figure out how many times bigger it is. I can find this by dividing the relative frequency by the theoretical probability, and I get an answer of 1.402. From this, I can see that relative frequency is almost 1.5 times the theoretical probability. And this leads me to believe that the spinner is unfair. This isn't the only way that this question can be answered. I could, if I wished, work out the expected frequencies of each of these colours if, again, the spinner was fair. We found these expected frequencies in example 2. And just to remind ourselves of how we worked these out, if the spinner was fair, then we could multiply the theoretical probability by the number of trials, which in this case is 600, since the spinner is spun 600 times, and that's where our 200 is coming from. If I was using expected frequency, then I could compare that value with the observed number of outcomes for that colour. And again, pink is kind of the prime candidate here for inspection because it's got the biggest divergence from the expected frequency of all of the values. And again, really what I'm looking for is how many times is 280 of 200 so that I can compare then what the discrepancy is. And when we calculate this, we get a value of 1.4, which is very similar to what we got previously when comparing our relative frequency and probability. In fact, the only reason there's a difference is because we rounded off our decimal places earlier. So our observed frequency is almost 1.5 times the expected frequency. So it's a lot bigger than it should be. And again, this leads us to suspect that the spinner is unfair. Just to point out that you don't need to take both of these approaches. One of them will do. But it is very important that you explain your answer by showing the calculations for one of those cases. One final possible approach is to compare within the observations themselves. Note that in our expected frequencies, pink, yellow and orange should all happen 200 times, again if the spinner was fair. But clearly some of the observed results diverge quite broadly. We can relate these by putting the observed frequency of pink, for example, over the observed frequency of yellow. And I'm choosing those two particularly because they're the highest and lowest observed outcomes. And when I calculate that, it comes out as 2. So actually the number of times pink happens is twice as many as the number of times that yellow happens. But if I look at the expected frequency of pink and the expected frequency of yellow, they should actually be the same. They should each be 200. So pink occurs twice as often as yellow when they are predicted to have equal frequency if the spinner was fair. And again, this leads me to the conclusion that the spinner is unfair. And again, just to emphasize here, you don't need to go through all 3 ways of showing unfairness that I've done here. I'm simply giving you different options for how you can approach the question.